Hi. In the previous video, we learned about optimization conditions. So conditions for finding relative minimum or maximum of the three-dimensional function. So the function of two variables. Okay, that looks like z too much. Now, so what we're going to do right now is that we're going to use them in practice. So we're going to see how to solve problems where we need to find maximum or minimum of a function of two or more variables. And look, this is the function that we've got here. So z is equal minus x minus 2 squared minus y minus 2 squared plus 2. Look, this is a case of extremely simple function. Why? Look, here, even without any calculation, I can tell you the result. Why? Look, as you've seen in our video about drawing three-dimensional functions using GeoGebra, this is the case of the upside-down parabola. So, because we've got minus on x squared and minus on y squared, right? Now, of course, we will have the spheric shape here because because this is in 3 dimensions. But look, we know that the maximum of this would be at 0, 0, 0. But here, on x it's moved by 2, on y it's moved by 2, and we've moved the function 2 units up. So the result we expect to get is 2, 2, 2. We start with an easy example like that just to see how it works, and we can then see whether our intuition on the solution here is correct. Okay, so we start with first order condition and we calculate partial derivatives, fx. So we need to calculate partial derivative of this with respect to x. Okay, look. When we will be differentiating, we treat y as constant, so this part is gone, and this is a constant, so we don't even need to take care about this. All we need to do is to differentiate this expression. And look, here we need to use integration by the chain rule. I'm sorry, integration. I was thinking about integrals. We need to use the chain rule of differentiation. So look, what is going to happen? 2 goes up front, right? Derivative of the outside function. And derivative of the inside function with respect to x is of course 1. So we get out of this negative 2x plus 4. Right? Because this 2 goes up front. And so when we multiply everything inside, here we will have 2 minus 1, right? We get negative 2 plus 4. And we equalize it with 0. And look, right away, we see that this is an equivalent to 2x equals to 4, or x equals to 2. Okay, now we calculate first partial derivative with respect to y. Now, this is a constant, this is a constant. We need to take care of this. And look, out of this we're also going to get negative 2, but this time y, plus 4, because minus is in front of everything, equals to 0. So we're going to get that y is also equal to 2. Okay, so now let's move to second order condition. Okay, our second order condition, of course, requires us to find a Hessian. Okay, so what do we need to do? We differentiate this with respect to x and with respect to y. Let's do it slowly. Here we have rho associated with first derivative with respect to x. Here, first derivative, partial derivative with respect to y. Here we differentiate with respect to x. Here we differentiate with respect to y. And look, first derivative, derivative of the first derivative with respect to x is negative 2. With respect to y is 0. If we have 0 over here, we will also have 0 over here because Hessian is symmetrical. It's a type of like we have the symmetric matrix in matrix algebra. And look, we clearly see that if I differentiate this with respect to x, I'm going to get 0. And now if I differentiate this with respect to y, I'm getting negative 2. Okay, so now we need to find the principal minors. The first principal minor, so when we cut out the first square, we're going to cut out here. So h1 is given by negative 2. h2, so the second principal minor, is the whole Hessian. So we get that this is negative 2, 0, 0, negative 2. And we see that this is 4 minus 0, which is 4. So because first principal minor is negative and second is positive, we see that our 2 points, x equals to 2 and y equals to 2, are giving us maximum. Now, what is maximum value of z? In order to get it, inside of z function, we have to substitute optimum x and optimum y, and we get that this is, out of this, we substitute 2 instead of x, we get 0. We substitute 2 instead of y, we get 0. And we get 2 at the very end. So we get that this is 2. So look, the solution to our problem is a triplet of points, x equal to 2, y equal to 2, and z equal to 2. Okay, now let's try another example. So now we have that z is equal to x minus 3 squared plus y plus 4 squared minus 5. Okay, again, I hope even without calculation you can guess what will be the answer, but let's try to do it anyway. So we start with first order condition. So I calculate derivative with respect to x. Out of this I'm getting that this is, using of course the chain rule again, 2x minus 6 equal to 0. And out of this I'm getting that x equals to 3. And then fy equals to, so derivative with respect to y is going to be 2y plus 8 equal to 0, and out of this one I'm getting that y is equal to 4. Okay, so now we're ready to move to second order condition. Second order condition of course requires from us calculation of a Hessian. Again, first row fx, second row fy, we differentiate with respect to x, we differentiate with respect to y. Okay, derivative of this with respect to x is 2. Derivative of the first derivative with respect to y is of course 0. Is 0 here, we need to get 0 over here. And we would if we differentiated this with respect to x. And then if I differentiate this with respect to y, I'm getting 2. So this is our Hessian. And again, we need to calculate its first 2 principal minors. So here we got the first one. So first principal minor is equal to 2. And the second principal minor, which is equal to the entire Hessian, is given by 2, 0, 0, 2, which gives us again 4. Because both of those are positive, we get that this must be a minimum. Which is again exactly with what we would expect from this. Now, what is the optimal value of z? So the minimum z can take? Well, this, of course, again, we should place here the values we've obtained. So for x with asterisk, y with asterisk. So we have a z of 3 and 4. And this, look, if I put 3 here, this is 0. If I put 4, oh my god, of course, it was negative 4 over here. My mistake, it's negative 4. Negative 4 over here. If I put negative 4 over here, it's 0. And with negative 4 over here 0, our solution is negative 5. Okay, so let's carry on. Let's try yet another example. And now let's try something slightly more involved. More challenging. Oh, that would be a good adjective. But it's really late. I'm running out of adjectives. Okay, so we've got that z now is equal to 8x to the power of 3, so 8x cubed plus 2xy minus 3x squared plus y squared and plus 1. Okay, now what do we do next? So we're going to start again with first order condition. So fx in this case is equal to 24x squared plus 2y minus 6x. Yes, and that's it. Okay, so we've got 0, and we equalize it with 0. Then fy is equal to 2x plus 2y, and that's it, right? 2x, 2. Okay. So look, what do we get out of the second equation? Out of the second equation, I'm getting that 2y is equal to negative 2x, right? And now I can easily take this result and substitute it over here, right? When I do it, our result changes into 24x squared minus 2x minus 6x equal to 0. So we've got 24x squared minus 8x equals to 0. And now look, if I'm going to take 8x out of the, maybe even 24x out of the parenthesis, I'm getting that this is equal to x minus 1 over 3 equals to 0, right? So, we get out of it two possible answers. Let's call it x1. The first one is if x is equal to 0, or of course we can have x, we don't need this. If we use x1, x2, then x2 is going to be equal to 1 over 3, right? Now, from here, we can actually read what is y going to be. Because look, I can solve this easily for x, and I'm getting that x is equal to negative y. Right, so if x is equal to 0, then y is also equal to 0. But if x is equal to 1 over 3, then y is equal to negative 1 over 3. Okay, and look, those two pairs of points are actually our candidates for maximum or minimum. Okay, so now to decide which one is which, again we need to resort to the second order condition. So we need to find a Hessian. We got fx, fy, differentiated with respect to x, differentiated with respect to y. Okay. So now we differentiate this first with respect to x. We get that this is 48x minus 6. If I differentiate this with respect first, for a derivative with respect to x with respect to y, I'm going to get 2. If 2 is over here, 2 is going to be over here. And of course it is if we differentiate this with respect to x. And now if I differentiate this with respect to y, I'm getting 2 as well. Okay, and look, this is actually showing us that this time value of the Hessian determinant depends on x. Like the case we didn't have yet, but of course it's not a problem. But it means that we need to consider 2 scenarios. Scenario number 1 is x equals to 0 and y equals to 0. Now what is happening over here? Okay, it goes like so. Our Hessian takes the form of negative 6, 2, 2, and 2, right? So H1, which is still first principal minor, is negative 6. Now, the second H2, so second principal minor, is given by negative 12, okay, minus 4, which is equal to negative 16. And look, because, actually, this could give us potential candidate for maximum, but because second principal minor is lower than 0, this is not minimum nor maximum. Actually, this is going to be an inflection point. But look, we are not going to talk about inflection points. Well, actually the saddle point, because in 3 dimensions it's called a saddle point. We're gonna skip it, right? And we simply reject the first solution. We know that this is not maximum nor minimum. Okay, now let's consider the case number 2. In case number 2, we've got x equal to 1 over 3 and y equal to negative 1 over 3. Okay, and now look, actually the only thing I need to change here is to change the first element in the Hessian, right? Because the rest we already have. So now the Hessian is going to look like. So look, we've got 48 times 1 over 3, right? I substitute 1 over 3 instead of x. So I'm getting that this is 16. 16 minus 6 is just 10. So we get 10, 2, 2, 2. Okay, so H1 in this case is equal to 10, which gives us a candidate for a minimum, and H2, which is equal to the determinant of the entire Hessian, is 20 minus 4, which is 60. And look, because both of those are bigger than 0, this is clearly a minimum. Okay, so this is very. So we're almost done. Look, what is the one last thing we should do in this case? Well, I'm not going to do it because there's too much calculations, and actually it's not that important. But remember, in the last moment of the exercise, once we found that those 2 points are corresponding to our minimum, what we should do is to take the z function and find the minimum value. So I would take and plot inside this function, put inside this function the 2 optimum values. So instead of x, I will be placing 1 over 3, and instead of y, negative 1 over 1 over 3. Okay, and actually I can tell you the result because the result, which we can write as this, is 1 over 3, negative 1 over 3, and 23 over 27. This is our minimum. Okay, so the next exercise we're going to do is going to be more economic. More in terms that it's going to be like application of what we've learned to an economic problem. Okay, so let's just say the profit function of some company is given by the following function. So we've got that the profit is equal to A times square root of P minus A squared minus P plus 6A. Okay, and look, let's just say P is price of the product and A is expenditure on advertisement. Okay, and look, we clearly can see that depending on those two, value of the profit of the company can vary. Okay, so we need to find the level of advertisement and price for which profit of this company would be the highest. So what do we do here first? Look, I always recommend this for you to do first. Let's change the square root into the power 1 over 2. So there's no confusion like that. Okay, and of course then we can move to first order condition. And look, we are first differentiating profit with respect to, let's just say price. Right? So I'm getting out of this that we're going to get 1 over 2 goes up front, A going to stay here, P to the power negative 1 over 2. This is gone because it's treated as constant. Now here we have minus 1, this is gone, equals to 0. Okay, so then we differentiate this with respect to advertisement, and so we're getting just P to the power 1 over 2 minus 2A plus 6, and it's equal to 0. Okay, you see, now the case is a little bit more troublesome, but with a little bit of arithmetics we can get rid of it. Look, I'm going to first deal with this part. Look, out of this I'm getting that 1 over 2, A, P to the power negative 1 over 2, is equal to is equal to 1, right? Okay, so first thing I'm going to do over here is to divide both sides. Multiply both sides by 2 times 1 over a. Okay, so what happens? This part is gone, so we've got p to the power 1 over 2, and over here we're going to have 2 over a. Of course, here we've got minus. And look, what do I need to do next? Look, I want to substitute the result over here. Here I have p to the power 1 over 2. So in order to get this, I need to take both sides of this equation to the power negative 1. So I'm getting that p to the power 1 over 2 is equal to a over 2, or simply 1 over 2a. Okay? And look, now what I can do is that I can substitute this result directly over here. So I'm getting that 1 over 2a minus 2a plus 6 is equal to 0. Okay, out of this I'm getting that basically the negative 3 over 2a is equal to negative 6. Or if I multiply both sides by negative 2 over 3, right, to get rid out of this expression, I'm going to get that a is equal to 4, right? Because look, I'm getting out of this like 3 and 3, so I'm just having 2, I'm having 4 over here. And this is the first part of our solution. Look, now I can very easily calculate what is p to the power 1 over 2. Because look, p to the power 1 over 2 is equal to 1 over 2a. And this is equal to 1 over 2 times 4. So 2. And look, now if I have p to the power 1 over 2 equals to 2, I take both sides to the power of 2, and I get that p is equal to 4, just like a. Okay, now those 2 points are our candidates for either maximum or minimum. Of course, we want to maximize profit. So we would be very, very happy if it would turn out that this is a maximum. Okay, but of course we need to check it. Okay, so okay, second order condition. Now I need to start by calculating a hash rate. So here we will have row devoted to d pi dp, and the second one devoted to d pi dA. And now I'm differentiating it with respect to p, differentiating with respect to a. Okay, and what am I getting now? Okay, over here, if I'm differentiating this with respect to p, again, it's going to be negative 1 over 4 a times p to the power negative 3 over 2. Now, if I'm differentiating this with respect to a, I'm going to get that this is simply 1 over 2 p to the power negative 1 over 2, right? And look, because we have this result here, the same one will be over here. And because those two are the same, of course, we clearly see that if I would differentiate this with respect to b, I would get the same result. And finally, all I need to do is to differentiate this with respect to a. This is negative 2. So, Now, the next thing, okay, let's do it right in the Hessian. What we need to do is to substitute the two values. No, it's going to be better later because we would repeat too many calculations. Okay, let's start by finding H1, right? First principle minor. Okay, so it is equal to negative 1 over 4 times A times B to the power negative 3 over 2. Okay, so how much is that? We get that this is negative 1 over 4 times 4, right? And times 4 to the power of 3 times 1 over 4 to the power of 3 square root, right? This is what we got out of this. Okay, those two cancel each other out. So we've got negative over and 4 to the power of 3. 4 to the power of 3 is 4 times 4 times 4, which is 64. Square root out of it is giving us 8. So we get that first principle minor of a Hessian is equal to negative 1 over 8. Negative 1 over 8, which is of course negative. Okay. Now, second principle minor of a Hessian. So we now take the entire Hessian, and now let's also already substitute. We know that this is equal to negative 1 over 8. Now, how much we're going to have over here? If I'm going to put here 4. Okay, let's calculate this part. So we've got 1 over 2 times 4 to the power negative 1 over 2. Or in other words, this is 1 over 2 times 1 over 4 square root of 4, right? I'm sorry, that looks so bad. Okay, 4. And well, this is just 2, so we get that this is 1 over 4. 1 over 4 over here. And finally, we've got negative 2. Okay, so now we calculate this all out. Look, this negative 1 over 8 times 2 gives us 1 over 4. And now minus 1 over 4 times 1 over 4, which is 1 over 16. And this is equal to, of course, 3 over 16, which is bigger than 0. Because first principle minor is positive and second is negative, we know that this point must be at maximum. Okay, very well. So the only thing we need to do over here is to calculate the profit. So, okay, this time let's do it. I don't think it should be that complicated. Let's see if it's, how much is it. So, here it is. A with asterisks times B with asterisks to the power 1 over 2 minus A with asterisk to the power of 2 minus B with asterisk plus 6 times A with asterisk. So, this is equal to 4 times square root of 4 minus 4 to the power of 4, which is 16, minus 4 plus 6 times 4 is 24. Okay, so this gives us 8. So we've got 32 minus 32 minus 20. This is 12. So this is the profit of our company. Okay. I know at this moment you probably know very well how to approach these problems. And I know it is getting longer, but there is one more exercise I would really like for you to do with me here. Okay, so let's try. So now let's try this. Okay, so we've got that z is equal to x plus 2ey minus ex minus e2y. Okay, and again, all we want to do over here is to find maximum or minimum of this function. The other, so saddle point is not interesting to us. We start with first order condition, and we get that fx in this case is 1, 0, minus e to the power of x, this equals to 0. Now fy is equal to 2e minus 2e to the power 2y equals to 0. And now look, out of this we get that e to the power of x equals to 1. To which power I need to take e in order to get 1? Of course, to the power of 0. Now, out of this, we are getting that 2e to y is equal to 2e, right? Now, those 2's are canceling each other out, right? And look, here we've got that e to the power 2y is equal to e, but e is the same as e to the power of 1. So what we get out of it is that 2y must be equal to, what we get out of it, which is in one direction, 2y is equal to 1, or finally this is giving us that y is equal to 1 over 2. Okay, we've got this. Let's move to the second order condition. Now we've got our candidate for either maximum or minimum, but of course now we need to check which one of the two it is. Okay, so we've got now second order condition. We calculate the Hessian first. Out of the first part, I'm getting out of the first derivative, I'm getting this is negative ex. Then 0, 0 over here, and out of this part, I'm getting negative 4e to the power 2. Right? Okay, and look, what is h1? Well, h1 is equal to negative e to the power of x. Now, the thing is, at this moment, I already know that this value here is negative. How? Look, it doesn't really matter what I replace instead of x. This is definitely going to be negative because e taken to any imaginable power, any imaginable real power is a number bigger than 0, but with minus at front, this is definitely negative. But in our case, this is e to the negative e to the power of 0, which is negative 1. Well, definitely lower than 0, right? Now, let's calculate the rest of the Hessian. So now we calculate h2. We get, instead of this, again, I'm going to write just negative 1. We've got 0, 0, negative 4e to the power 2y. If I multiply those, I'm getting that this is 4e to the power 2y. Again, even at this moment, I already see that this is positive, right? But if I replace our value, I'm getting that this is 4e to the power of 1, which is 4e. This is definitely bigger than 0. Okay, so finally, that we know that first principal minor is negative, second one is positive. This must be maximum. And what is even more, we now see, and now we see that we can actually calculate the maximum value of z. So how much is that? Now we replace x with the x we calculated, which is 0. So first component is 0. Then y is 1 over 2, right? So 2e times 1 over 2 is just e. Then minus e to the power of x, 0, it's negative 1. And minus 2e to the power of 2y, so e to the power of 1, so minus e. We get that this is equal to negative 1. So our solution is a triplet 0, 1 over 2, negative 1. Okay, look, those examples that we did just now are actually touching all the problems which you might encounter during all the exercises that I also devised for you. So, I think this is it about three-dimensional function. In the next video, we're going to move the ball one step further. Because what we are going to do is we are going to see how to find a maximum of the function with n different variables. Okay, thank you for your attention and see you in the next video.